Okay, so I'm going to do this vector example, one of the book problems from Serway. So you've got a radar station locating a sinking ship at a distance from the radar station to the sinking ship is 17.3 kilometers, 136 degrees clockwise from north. And then from the same station you locate a plane which is horizontally 19.6 kilometers away and 150 degrees clockwise from north. So the first thing to do is to draw a picture. So I've drawn here north, south, west, east axes. The radar station is at the center of the coordinate system. You can see my coordinate system is given up here. So I hat points east, j hat points north, and k hat is pointing upwards, sort of out of the page, sort of up away from the center of the Earth. And then I've drawn two vectors on here, the ship and the plane, and I tried to draw them sort of roughly the way that they should look. So, theta p is larger than theta s, and then the vector for the plane is longer than the vector for the ship. So you notice in my sketch here, I drew these angles theta s and theta p. Those angles are measured from the east axis. That's just the way I like to do it. So those angles are going to be different than the ones given in the problem. Theta s and theta p for me are going to be 46 degrees and 63 degrees. And they're different from by 90 degrees from the ones given in the problem, because the ones given in the problem are clockwise from north, right? And the ones I'm giving are measured from the east axis. So that's just how I'm going to do it. And then I've labeled here the distances. So rs is the magnitude of the vector from the radar station to the ship. That's 17.3 kilometers. rp is 19.6 kilometers. And then there's this zp, that's the sort of height at which the plane is flying, 2.2 kilometers. All right, so let's work on part A here. Part A is write the position vector for the ship relative to the plane. So that's kind of important, relative to the plane. What does that mean? So that means that if I'm on the plane, what is the vector that goes from the plane to the ship, right? In other words, what vector should the plane fly in order to, help the people on the ship who are sinking? So if you think about it, what I need is a vector that goes from the plane to the ship. So I'm drawing here a vector, which I'll call delta r. That's the vector that goes from the plane to the ship. So the vector delta r and the vector r plane are tip to tail, right? So if I add those two vectors, r plane plus delta r, I get to the ship. So in equation form, that triangle that I drew, rp plus delta r, is equal to the vector for the ship, right? And I want delta r, so if I write this a little bit differently, I get here rs minus rp, and I want this vector, right? This delta r, that's the target. I want the vector that goes from the ship, from the plane to the ship, and that's the expression for it. So all I have to do now is write down vectors for the ship and for the plane and subtract them. Okay, so let's just do that. Let's do rs. I'm going to write it like this. Magnitude rs cosine theta s, this is the x component, I hat, minus rs sine theta s, j hat. Okay, so remember that these rs, this here, rs, is the magnitude, right? That's a positive number. That's 17.3 kilometers. So the vector from the picture clearly has a positive x component and a negative y component. That's where this is minus sign here, right? So I put in the minus sign because that vector rs has a negative y component. Okay? Okay, now let's do the same thing for rp. It's very similar, has a positive x and negative y component. The only difference is I need to change all the s's to p's, and I need to change, well, there's a z component for the plane, which I need to add. So I'll put here rp cosine theta p, I hat, minus rp sine theta p, j hat, plus zp, k hat. So there's my vectors for rs and rp. And all I have to do now is subtract those, right? Delta R, that's what I'm looking for, is RS minus RP. So I'll do that on the next slide. I'll just kind of subtract those two vectors and plug in the numbers. Okay, so now let's continue working on part A. The thing we were after was this vector delta R pointing from the plane to the ship, and we had worked out that the formula was delta R is RS minus RP. We had written down formulas for RS, so this here is RS, and this here is RP. So now all I have to do is subtract those two. Just remember how to subtract vectors. I subtract the components separately. So let me just rearrange this a little bit. So I'll put the I hat components together. I'll have RS cosine theta S minus RP cosine theta P I hat. That's the X component. Now for the Y component, I've got some extra minus signs. RS sine theta S plus, so there's a plus because there's a minus here, but then there's also a minus here. So I have plus RP sine theta P. That's the Y component. And finally I've got the Z component, which is just ZP K hat. So that's basically the formula for this part A. That's the vector that goes from the ship, from the plane to the ship, or the vector for the ship relative to the plane. And now to get a final answer, I just need to plug in the numbers. So I need to plug in all of these numbers into that formula. And so I will sort of skip over the details, and I'll show you the answer on the next slide that comes from plugging in those numbers. So here's the results when you just plug in all of those numbers up in the right-hand corner into that formula. You get, this is your result for delta R. So that's the vector that we're after. Take a moment to see whether this makes sense. So the vector that we have has a positive X, positive Y, and negative Z component. If you remember what the picture looked like, there was the plane here and the ship here. So that was the, sorry, other way around. This is the ship and this was the plane. And the vector delta R was the one that went like that, right? And that clearly, sorry, this was north, south, west, and east. That has a positive X and a positive Y component, that vector. So that agrees with our answer. And then it makes sense that it has a negative Z component because the plane has to fly downward towards the water to get to the ship. So at least the signs make sense. So it passes that. So always ask yourself if your answer makes sense before you sort of move on. So that's the answer to part A. And then for part B, we'll just go to the next slide to continue the problem. Okay, so now let's start thinking about part B. Part B is just asking how far apart are the plane and the ship. We've worked out in part A the formula for the vector, which points from the plane to the ship, and that was given there, right? And so now, how far apart are the plane and the ship? This is an easier problem, so now it's just asking for, what I want is the length or the magnitude of that vector delta R. So this is my target, just the magnitude of the vector that points from the plane to the ship. So this is now my target. And that's easy enough, right? I know how to take the magnitude of a vector since I already know the X, Y, and Z components. So I just need to write here, I'll just take the components and use the sort of three-dimensional version of the Pythagorean theorem. I'll say delta Rx squared plus delta Ry squared plus delta Rz squared. So just add up the components and square them, take the square root, and that'll be the answer. So now all I have to do is just plug in numbers into this, and I'll do that on the next slide and just show you the answer that comes out of it. So this part is pretty simple compared to the previous part. So I'll go to the next slide, show you the answer, and then the problem is solved.